So we want to find convergence and divergence of series. Okay, we want to end up with series. Now, up to now, we just started today with looking at sequences, and those are important because for a series to have a chance of converging to a limit, the nth term or the infinite term of a sequence must be equal to zero. So when we're adding up a whole bunch of terms, if the terms don't go to zero, we're just going to be adding an infinite number of finite terms, which is always going to be infinite, which is divergent. And we are interested in convergent series. So this is important to establish is that the limit of the sequence must always end up at zero. Okay, the last term of the sequence or the infinite term of the sequence must tend towards zero. Now that's our basics. That's once we pass that, then we can start looking at other things to determine convergence and divergent. So to apply convergence and divergence to series, we want to have some references that we can work with. So we're going to look at ones that we've already defined. The first one is the infinite geometric series. Okay, the infinite geometric series is one that we looked at in grade 12, and it is AR to n power n minus 1. Now that always has a limit. Those always have a limit as long as our common ratio or our multiplier is between -1 and 1, which means that every term is getting smaller and is tending towards zero, and it's getting smaller fast enough for it to converge. And that one, we happen to have a formula to calculate that limit. Now, most of them, we're not going to be able to actually calculate the limit. We're really just interested in convergence and divergence. But for the infinite geometric series, we happen to have a formula. So that's one. Another one is that we looked at is the harmonic series. And this is important because this is kind of our boundary series. And it's a boundary between convergent and divergent. So 1 over n, as we add up those terms of the series, adds up to infinity, and so it is divergent. When we have our p series from the harmonic series, we can just expand that a little bit and just say, well, power is 1 on the harmonic series. When the power is not equal to 1, in fact, if it's greater than 1, it will converge down to 0. The terms go to 0 a little bit quicker, and which means that the sum is going to be a little bit smaller, and that allows the sum to be finite. So we have a limit for that. So it is convergent when the power is bigger than 1, and the reverse is true as well. When the power is less than 1, or we have a root, that's going to end up being divergent because it's going to go to 0. The terms will go to 0 slower than 1 over n when we compare those two. So if the harmonic series is divergent, the p series when p is less than 1, that will also be divergent. And lastly, the one that we have looked at is the alternating harmonic series. And the alternating harmonic series, because it alternates, it happens to be convergent. And this one, if we take a look at what happens, if we have a positive term, so if n is equal to 1 and it's positive, okay, we're going to end up going from, we can just show this as this is equal to 1. It's going to be equal to 1 like this. Okay, the next term is negative. We subtract. We're going to add in 1/3, something like that. And we're going to add in 1/4 or subtract 1/4. We end up something like this. And what ends up happening is it will never break outside those bounds. So it's always going to go not quite as far as the last one. And what ends up happening in that case is it starts to converge to a limit. And that limit is going to end up being equal to, it just happens, again, for most of these, we can't calculate the limit, But we just happen to be able to calculate the limit of this one, and this one happens to be log 2, which is approximately 0.69.